Okay, so let's get started. Maybe one more minute. Only half the class is here. So are there any questions? No. Okay. Have you started on your next homework? Oh, you have? Okay, I thought I was just joking, but that's good. That's good. Yeah, this one is going to be a little bit more work than the previous ones. And but I think what I can say is that these I'm not going to be handing you multiple midterms to look over for the next midterm. Okay, so your homework problems should be enough to prepare you for the most part. Okay, so there may be some topics, but certainly on the topic covered in this homework, you are not going to need any other material, right? So there are plenty of problems in the homework that was handed out to you. Okay, so let's pick up from where we left off, and I would, can I see more of you? So I have a, I can see that it is not a 10% class and more of a 50% class. So so we've been spending most of our time sort of working out problems in this counting unit, and that's what we are going to continue to do today. Okay, so let's try to answer this question. So how many numbers between 1 and 100 contain a 5 in them? Anybody wants to try?
Is it an infinite amount?
1 and 100.
Or no, we're talking about just integers, or
Yeah.
well,
Just
oh, okay,
counting.
10.
So we are
10?
counting. In counting, yeah, we will not think about all the rational and real numbers. No, that's part of the.
Got it. Okay, then 10.
Okay, so another answer.
Or 9. I forgot. See draft.
18.
18. Why 18? Is it not 19?
Yeah, I think it's.
Oh, I think I missed one. Yeah.
Okay. Anyway, so basically, the first mistake we make, of course, the answer that we would immediately think of is 9 or 10, right? Thinking about all, like 9, 19, 29, and so on, right? Or no, 5, I'm sorry, 5, 15, 25, and so on, right? And then we forget that 50 through 59, all of them have a 5, right? So you add that 10, but then you will say 20, but that's not correct. It is 19, right? Because if we count this 10 plus that 10, then 55 will be counted twice, okay? And by the way, that's another instance of the inclusion-exclusion principle, right? So what the exercise we went through is we took the set of numbers that have 5 in the ones position, right? So let's say S51, they have a 5 in a ones position, and then we tried to do a union of S5 in the tens position, which I'll just call it as 2, the second digit. And if these were disjoint, then we could have added the sizes, and then this is 10, and that is 10, and so we could have said it is 20, but it is not a disjoint union. So what we need to do is we needed to do S51 plus S52 minus, right? So the numbers that have a 5 in both digits, right? So that is being double counted. So if we apply the inclusion exclusion principle, that'll tell us, hey, the number is 19. But that's kind of a side point because we won't, using inclusion exclusion principle is not the best approach for solving the problem. But it's certainly something to keep in mind that, all of these rules are applicable in many different situations. In some situations, those rules are, give you the answer more easily than in other situations. So let's try to make this a little bit more complicated and say, how many numbers between 1 and 1,000 contain a 5 in them? I mean, can anyone try? Again, you don't have to tell me the number, but you can just tell me this is how one would go about it.
Would it be something like,
Yeah, Kelly?
Well, based on 1 to 100, there's 19 through each 100, but you have to consider the 500, like
Right.
kind of group. So that's like a bunch.
Right. So we could again do this, S51 plus S52 plus S53, and we can apply this inclusion exclusion principle on 3 sets, which is even more complicated, right? So this is the inclusion exclusion set, rule on 3 sets, which means that you have to compute S1. Each of these is going to be 100, right? Because if you keep one of the digits fixed, then the remaining 2 digits are going to be 100 possible values, right? So each of these is 100, and then each of these will be 10, right? Because if you let 2 digits be 5, then the other digit can vary in 10 ways. And then if you say all 3 digits are 5, then there is just 1, right? So you can do this, and that'll give you 300 minus 30 plus 1. So that seems like 271 seems to be the answer. Okay. So, but this is not how we would do it, because there is actually, this way obviously doesn't scale, because if I say, right, if I ask you this, surely this approach is not going to, it's not that it is infeasible, but it is going to take you like half an hour to do the problem. If I said, how many numbers are there between 1 and 1 billion containing a 5 in them? So we have to think of a different approach. Can you think of what might be an alternative approach? Greg?
You could consider using the results from the previous iteration, like to find for the number of numbers between 1 and 1,000, you could use your result from 1 and 100 and then modify it, like a linear transformation.
But if you want to do this for 1 and 1 billion, how do you do that quickly, right? Like, for instance, it shouldn't take the rest of the class, right, to do the calculation. So how is there some way we can do this quickly? So inclusion exclusion principle is just one of the, Owen, you want to try?
Could you use the fact that, like,
each digit has a 9 out of 10 probability of not being a 5. So you can find the probability that there are no 5s and then do 1 minus that.
You could try that, but I'm sure it won't give you the exact number, right? So to get an approximate number, right? We can do that. On the other hand, you could say that approximately, yeah, the approximate calculation is easy to do, or rather easier to do. Okay, so there is another property of sets that we can utilize, which is that size of A equals right. So we can count the size of the complement, right, and then subtract that from the universal set, and that'll give us the number we are seeking, right? So in this case, let's look for the numbers, right? Here, the universal set is, every number between 1 and 1 billion, right? So we have this from the definition of the problem, the set of all numbers, the universal set that we are considering is 1 billion, right? So this is the set that contains at least 1 5, right? So what would be the complement set? Brian?
None of the numbers contain any 5s.
Right. So no 5s, right? So how many such numbers are there if you cannot have a 5? So a billion has 9 digits, right? 9 zeros, right? So how many numbers without a 5 are there? Simply 9 to the power 9, right? Because each digit can be chosen in one of 9 ways, right? Because you took away 5. So out of the 10, there are only 9 ways, right? So you take that away. So all you have there are 9 to the power 9 numbers that don't contain a 5, right? So therefore, 10 to the power 9 minus 9 to the power 9 gives us all of the numbers that contain at least 1 5 in them. Right? So again, this is a strategy that you might have used in the past, right? Instead of counting, how many people or how many things have a certain property, you look for the set of the number of people or things that don't have the property, and then you just simply count the remaining, right? So instead of looking for numbers that contain a 5 in them, we simply look for the numbers that don't contain a 5 in them, and that set happens to be much easier to compute, right? And then we get a very quick result, like 9 to the power 10 to the power 9 minus 9 to the power 9. So you can certainly see that if you apply this formula, which basically says 10 to the power n minus 9 to the power n, if you're looking for n digit numbers, right? Then the formula would be 10 to the power n minus 9 to the power n. And we certainly got that right for n equal to 2, right? So that would be 10 to the power 3 minus 9 to the power 3. I'm sorry, 10 to the power 2 minus 9 to the power 2, which is 100 minus 81, which is, okay, let me just write this down. So 10 square minus 9 square equals 100 minus 81 equals 19, right? So we got that right. Did we get it right for 3. Yeah, we made some mistake, right? So this is I think a much larger number. So we must have made a mistake before. But this calculation is correct, right? So so again, sometimes you have to look for the complement of the set. So let's look at another problem. There are six books on the shelf, and you want to pick 3 books such that you don't pick any consecutive books. Okay? So how can we try to do that? This is not a hard problem as it is posed. Of course, we are going to make it harder, and then we have to come up with a better way of counting. But as it stands, this is not very difficult to count, right? So you can just try to enumerate because it doesn't look like there are too many, right? So let's say we pick the first book, right? If we, Kaylee, you want to go ahead? I'm sorry, I didn't. Yeah.
I think you can just choose every other book. So if you choose the first book, then you
Right.
choose the third, and then the fifth.
5, right? And then we can do 1, 3, 6. Then you can also do 1, 4, 6, right? And that's it, right? Or we can do, then we can, of 1, we can try 2, and we can do 2, 4, 6. Did I miss anything, or these are the only 4? Okay, so maybe we got it right. What if there are 25 books and you want to choose 10? Or 6 for that matter. It doesn't, you know, the bigger factor is how large this is, right? So if it's 25, then whatever we are doing is not really going to work because there are just too many combinations. So what other trick can we use to count in this case? Unfortunately, it's not the complement trick. The complement trick definitely, you know, works for, you know, problems like how many numbers are there with the digit, right?
Does
So
it involve factorials by any chance? Not factorials, sorry.
No,
Um,
ultimately, most problems will involve factorials because ultimately we will reduce it into some n choose m type of thing. So ultimately there will be factorials for most problems. But we need to sort of figure out the previous step. How do you even convert it into one of those, you know, n choose m problems? Was there somebody else trying to answer? Okay, so remember the trick we used for counting ways to fill a box of dozen donuts, right? So what we were doing was we were saying, let's somehow map it into a binary string containing 0 or 1, right? And instead of just thinking about it as a binary string, the important point is to think of that binary string as a recipe for what you are doing, right? So in the case of the donut problem, the binary string was explicitly spelling out a process for selecting donuts, right? It was saying that if it's a 0, pick that donut, right? If it's a 1, then go to the next group, right? And then when you see a 0, pick more donuts from there. When you see a 1, go to the next group, right? So that's what, so essentially that 0, 1 string was giving you a procedure for how to pick. Okay. Can you think of how we might be able to use like a 0, 1 string and have it mapped to a particular way of picking books here? Michelle.
Could it be that like the zeros would be like you take a book and then you take the consecutive book, and like a 1 would be like you skip a book?
Okay, so we could definitely do that, but I think there may be some. So the condition is that once you pick a book, you have to automatically skip the next one. Okay, so I think maybe you got something. You may not have understood the problem exactly, but that didn't really affect the correctness of what you said. It's roughly that's the idea. Sam, do you want to refine that?
Sure, I'll try.
Yeah.
So when you pick a book, let's say all the books are starting at 1. You pick
Mhm.
one. You pick one of the books.
Mhm.
Then all the books. So the books next to it, both
Mhm.
books left and right, if there is one on the left, would be 0 then, because you cannot choose from them, right?
Correct. But we don't. We would prefer. Okay, so here are some simplifications you can do, right? So if you are picking this book, right? Assume that everything you have done so far is right. Okay, so if you're picking this book, you're already past the previous book, right? So let's not worry about. So we hopefully, if we did our job right until this point, we don't have to look at the previous book. We only have to worry about the next book, right? So we can say that whenever we pick a certain book, we will automatically skip the next one, right? So the string doesn't have to tell us the next step because the next step is implied. Okay, so what we are going to do is I'm going to say that we are going to use a 1 to tell us to pick a book and 0 to skip. Okay, so binary string of 1s and 0s, and 1 says pick current and skip next, and 0 says skip current. Okay, so how many bits, if there are 25 books, how many bits do we need to tell us exactly what to do? Greg?
15 bits.
15 bits. So I'm sorry. So it depends on how many you have to pick, right?
Yes.
So you are saying that we need 15. Can you tell me like a formula so we can understand? So let's call this N. Let's call this K, or maybe I'll just call it M.
I think we just need n minus m bits because for every m we choose 2 books. For like every 1 bit will give us 2 books, so we only need 1 more for the zeros, and that would satisfy. I think that comes out to n minus m.
So I think the answer is n minus m plus 1. Okay, so you can work through the details, and then you'll probably find that there is a. So again, before I jump into this one off, so the idea is that each one is already going to tell us to skip the next one, right? So therefore, each one is going to account for 2 books, except the case where you're picking the very last book, right? If you're picking the very last book, right? So you have to reach the last book. So if you think about it this way, so if you're talking about a binary string with 10 ones, right? Because we want to pick 10 books, so it should have 10 ones, right? And then according to Greg, according to what you said, you will have only 5 zeros, right? So, and a calculation would suggest that 10 ones will allow you to pick 10 books and skip 10 books. So a simple calculation says this will cover 20 books and this will cover 5. And so you have only 25 books to cover. And so you are covered everything. But the only catch is that the book you want to pick may be the very last one, in which case that one is not able to account for 2 books, right? Because it's not going to say there is anything to skip. And that's why you will need this +1 extra, okay? But again, for a problem like this, just as in the donut case, you can see that there is a way to map this onto a binary string with zeros and ones. And, you need this many zeros and this many ones. And now, can you tell me what is the formula? So now that we have said it is a binary string with, in this case, 16 bits and 10 ones, right? So what is the number of such numbers? A binary string of length 16 with 10 ones. Well, this is a simple problem, right? We are just picking, there is a string of zeros and ones. We are picking which subset of those positions are going to be 1. Brian.
Is it a 16 choose 10?
Right, so this is because there are 16 positions in the binary string, and we have to decide on which 10 are going to be ones. And that is essentially the definition of 16 choose 10, right? So that's how we solve this problem. Okay, so let's look at a different problem, but this is a problem that you have seen already, right? How many binary relations are there from a set X to set Y? Okay, so when we were thinking about cardinalities of sets, we talked about what are the, we discussed what is the cardinality of, so we, I think one example was we said, what is the cardinality of the set of all binary relations on N, right? So so we have done this before. So can anyone take a shot at answering this question? So how do we go about answering this question? So how can we, what is a relation? A relation is what? A relation is a subset of the Cartesian product of X and Y, right? Okay, Owen.
So would the number of relations just be the number of possible subsets, which would be the cardinality of the power set of X cross Y?
Okay.
So two to the.
So the number of relations. So if this is, so if every subset, right? So we need to be sure that every subset defines a separate relation, which is pretty obvious. So therefore, if every subset of X cross Y is a relation, the number of distinct relations should be, the power set of this, right? Because we are saying that every subset, right? So it's going to be 2 to the power right? Or if, which is 2 to the power x multiplied by y, right? So if x has a size of n, y has a size of m, then we have 2 to the power nm possible relations. Okay, so let's go through step by step. We know that each relation is a subset of x cross y. Therefore, every subset of x cross y represents a unique relation. Okay, and then
Question, Professor?
yeah, sorry, yeah, go ahead.
Is 2 to the nm, is that all binary relations or all relations in general?
So it's a binary relation because we are counting relations from x to y.
Okay,
Right?
so it's not, okay.
There are only 2 sets involved, so that's why it's called a binary relation.
Got it.
So every subset of x cross y defines a relation. So we want to find out how many subsets of x cross y exist, right? And the number of subsets of a set is really the same thing as the cardinality of the power set. Okay. So, so that we have counted, but this one we haven't done in the past, right? And so you remember that, for instance, we would have said that we had a homework problem where we looked at functions on natural numbers, and we proved that the number of functions on natural numbers is uncountable because it's kind of like the power set. Okay, and we also said that the number of relations on natural numbers is also uncountable, right? And we'll get uncountable from starting from natural numbers only if we did a power set construction, right? So naturally, so that's how we did it before. Okay, so now let's look at bijections, right? So we have a finite set of size n. So we want to count how many distinct bijections are there from x to itself. Okay, so again, remember bijection means, one-to-one total function. Okay, so if it has to be one-to-one, of course, that means that the cardinality of the 2 sets have to be the same. So how could we count this, right? So it is a function, which means that if you, let's take an example, right? Let's say okay, so because it's a total function, there so because it's a total function, there must be at least one arrow coming out of each of them. And because it's a function, that means there can be at most one arrow coming out, right? And it's a one-to-one, which means that there can be one arrow coming into each. So for instance, one bijection is this, right? So one way to capture this bijection is to say, I'm going to list it as a sequence where the first element in the sequence is going to be where the arrow from A points to. Okay, so this particular thing is going to be written as A, C, B, right? So this is, think of it as we are writing out f of a, f of b, and f of c, right? So the bijection, let's say the bijection that we are working on, let's call it an f, right? So what we are going to do is we are going to summarize the bijection by simply writing down the image of A, B, and C. Okay. So if we write it down this way, now we can say that every distinct string here, right? So A, B, C, or B, C, A, right? Each of those defines a different function, right? Because if this is F, maybe this is defining, let me call this F1, right? So this is defining a function F1. This is defining a function F2. This is defining a function F3, and so on. Right? These are all different functions because obviously, no two rows are identical, right? Which means that the functions differ at least at one point, right? So maybe they differ in the first position or the second position or the third position or the nth position, right? So this gives you n factorial, right? Because how many such sequences are there? Right? So every sequence taken from this set, right, corresponds to a separate function. And so if X has n elements, then the number of possible sequences here is going to be n factorial, right? So this is something that we know. If there are n elements, the number of possible permutations of n elements is n factorial. Okay, so n factorial is the number of bijections from X to X. Any questions?
Yeah. So we're discussing this in chat, and I'm just still kind of confused.
Yeah,
Maybe I'm just so I thought it would be n squared
okay,
because you could go a b a c b a b b b c c a c a c b c c. Apparently not. I was just confused why that doesn't apply.
okay. So let me try to understand what the
I see. Got it. Of a size of permutation of entire list of size n.
because I don't know exactly how you get the n square, right? So
Yeah,
you're getting
I
n square
did.
using some process, and I haven't understood the process by which you are generating possible functions. Because if I understood, I could tell you, okay, what is that you missed.
Got it. Okay.
So can you list your?
Yeah, I was thinking like you can map A onto A, or A onto B, or A onto
Let's
C.
just write it down like this, right?
I
So
see what I did wrong.
A.
Never mind. I
Okay.
see where I got wrong now. Thank you. I just
Now, sometimes even if you saw what is the reason why we might still want to go through it is because often, the confusion that we have is the confusion that somebody else also has. So you can tell me what it is, and we can still go through it. That might be helpful for everybody else. Or not. That's okay.
wait. Sorry, I was responding. What did you say? Sorry.
So what I'm saying is that if you can go through
what I was thinking.
Where,
Got it. Okay, so I think Greg probably put what I was thinking best. So he said we want permutations of an entire list of size n. We don't want a set of pairs of size 2.
Yeah,
that's what I was thinking. I was thinking set of pairs of size 2.
And I understand. You're talking about what are the how many distinct pairs can be formed.
That's what I was looking for. Yeah.
Right. And yeah. So if you just look for how many distinct arrows can be there, right? So that is n square, right? There are only n square possible arrows, right? But if bijection is a set of arrows, and therefore you have, you have to look at the entire set at a time, and that's why you get many more than the number that you have. Okay, because every permutation here corresponds to one set of arrows going from left to right that represent a bijection. Okay. Let's look at another problem. Okay, so so how many ways can we take an integer and break it up into k pieces, right? K parts, so that they all add to something less than n, right? So for instance, one example could be, let's say, if you set k equal to 2 and n equal to 3, okay? So then even this is too many. Let me just say 1. Okay, n equal to 1 and k equal to 2, right? So the possible ways are, let's write down x1 and x2, right? This is what we're going to write. Okay, so 0, 0, right? So then x1 plus x2 will be 0, which is less than 1, right? So we want to find, we are looking at a special case where x1 plus x2 less than or equal to 1. Okay, so if we set x1 to be 0, x2 to be 0, that's one possible answer. 0, 1, 1, 0, right? So those are the three possible ways of achieving a sum less than or equal to 1 using two integers, right? So this is the problem that we are trying to solve. How many ways you can split an integer into k pieces such that the k pieces add up to something less than or equal to n. So how could we count? How could we measure this? How could we figure this out? Okay, let's do the slightly different version of this problem where we don't look for less than or equal to n, but just equal to n. Haven't we seen this problem before? No? Think, we have seen it before. It's one of the problems that we have looked at. Anybody wants to try? There are only a few problems that we have discussed multiple times for me to expect you to remember the problem itself, right? So now it's just a matter of guessing among the 3 or so problems that we may have looked at multiple times. It's a donut problem, yes, right? Xi represents the number of donuts of the ith flavor that we want to pick, right? Okay, so it's the same problem. So therefore, the same solution would work. Okay, so now that we recognize that, right? So this is the number of donuts of the first type we want to pick, the number of donuts of the second type we want to pick, all the way to the number of kth donut we want to pick up, right? So this is exactly that problem, right? So let's take something slightly different. Okay, so now what do we do here, right? If it's less than or equal to n, how do we solve that problem? So when you see something like this, what you want to do is that, hey, this problem looks so close to this other problem. Can I somehow use what I know about that problem and kind of map it to this problem, right? So can we do something so that this equation can become more like that equation? Right? Is there a way to turn this one into this one? Greg.
Maybe we can use a summation and sum to different values of n.
I am not sure that I understand what you mean.
We would sum over all possible solutions to equals to n minus 1 equals to n minus 2 down to 0. I mean down to 1.
Yeah, but that won't tell us how to solve this problem, right?
I wasn't sure. Just trying to throw out an idea.
Okay. No, I'm sorry.
Yeah,
I understand what you're saying. What you're saying is that simply take this and say set it equal to 1, set it equal to 2, set it equal to 3, and so on, right? So it's a perfect, So we are all, on the one hand we try to do math, on the other hand we try to program, and the programmer in us immediately tells us this is, we write a loop, right? Makes sense, but there is just a very simple mapping from this problem to this problem. Okay, so all you need to do is you need to introduce one more variable, right? So if there exists x1 through xk that's less than or equal to n, that means there exists right? These two are equivalent, right? Because if this value is less than n, then whatever is the difference between this value and n can be captured in this xk plus 1. Right? So all we need to do is to introduce that one variable. Sometimes in some context, it's called a slack variable because it kind of picks up that difference. Okay, so we can easily map this into this, and this is the donut problem. Okay. What about this one? So we want to find k integers that are in increasing order such that all of them are less than or equal to n. Okay. It kind of looks similar to the problem that we saw just now, right? Kind of looks very similar in structure. So can we map this problem into one of the problems that we just saw? remember the problem that we saw was right. So this is the problem that we figured out how to solve. Can we use that to solve this problem? Michelle.
Would you like add like do like y1 plus y2 is equal to y2 plus y3, which is and like continue that?
Yeah, so it is the addition. So this is y1, that's y2, y3, and that is yk, right? So if we map the partial sums here, right? So x1 can be the same as y1, x1 plus x2 can be y2, x1 plus x2 plus x3 can be y3, and so on, right? So there is a mapping between, so it's just simply, this is telling you what is the size of the partition, right? And the y version is telling you, okay, so if you think of the zero, mapping the problem into a binary string with zeros and ones, right? So the x1, x2 version just says, okay, I have 3 zeros and then a 1, and then I have 3 more zeros, I have 2 more zeros. Whereas this version is simply telling you that the 1 appears in the 4th position and then the 7th position, or things like that. So this is always counting the position of the ones from the leftmost edge, whereas when we talk about x1 plus x2 plus x3, those x's are telling you how many zeros are present when we think in terms of the binary string. Okay, so it's just two different ways of looking at the exact same information, and therefore the solutions are exactly the same. Okay. I think that brings us to the end of this unit. So we will go on to the next unit, which is, so a lot of problems that you will solve in your homework are going to be somewhat similar, right? So of course you have to see this kind of connection, and the connections that you have to see are not going to be that difficult or that unintuitive, because we have already seen several such connections, right? So you certainly should go through the problems that we have solved in the lecture itself and try to connect them to the ones that you're going to see in the homework. Okay, and then you hopefully that'll help you solve it. And of course, you again have the due date has been marked as the end of next week, I think, right? So I'm very poor at remembering dates and no, I shouldn't say numbers. Very poor at remembering dates. So whatever it says, when I post something, I know exactly what I'm posting, but I don't remember now exactly what the dates are. But you certainly have the next Tuesday's recitations. So make sure that you make good use of that recitation for your next homework. So let's spend the remaining 25 minutes on, we can go to the next unit, which is probability, right? So counting feeds into probability because many times, even during counting, we often asked, what is the probability of something? Like, for instance, what is the probability of finding that a random number, with certain number of digits has a 9 in it, right? So this is a kind of a, and the way we solve the problem is simply counting the number of possibilities and then saying that, so essentially the first step to solving many probability problems is counting. So let's start with how many of you have heard of the Monty Hall problem, or not necessarily that you should have, but some of you may have. Anybody? Good. So anybody watches, you all of you are probably too young, but there's a show called Mythbusters, which ran for many years, maybe like 20 years, and ended in like early, like 2015, something like that, or maybe 2013, I don't remember. Do any of you watched that show? Okay, so one of the last few years they went through this problem, except that this problem has a very simple mathematical analysis, but they thought the mathematical analysis was too much for their audience, so they just did it experimentally, which to me it's not very convincing when you just do it experimentally, because if you repeat an experiment a very large number of times, then you can trust the results. But sometimes, when you actually have people doing things, it's difficult to repeat it, the experiment many times. So let's see what the problem is, right? So you're in a game show, and so it's a game show where you can win a car. And what you need to do is, there are 3 doors, and you need to pick the right door, right? So if the door you pick has a car behind it, then you win the car, okay? So but the host wants to increase the odds of you winning the car, or maybe not. But the way what happens is that once you pick a door, the host opens one of the remaining doors, and then shows you, look, there is no car there. Okay, now that you know what is behind one of the doors, right? Now you're no longer dealing with 3 unknown doors. You already know now one of the doors has a goat behind. So the host asks you, now that you have seen where the goat is, do you want to switch? Okay. So the question is whether you should switch your choice at this point, or should you stick with it, or does it really make any difference to your winning probability? What do you think? No, you don't get to win a goat. You can only drive a car back.
Don't you stay with the door you chose?
What you're saying is that there is no advantage.
There is no advantage, really, because you now both doors have a 50-50 chance. So I might be right. I don't remember quite how this when it played out, but
so the other theory is that when you didn't know where it was, right, and you picked a location, so you had 1 in 3 chance of being right. Okay. Now, if you pick again, now you already know that there is a goat behind one of them. So now if you just completely forget your choice and remake your choice, you seem to have a probability of half of picking the right one, right? So originally, your probability seemed like one third, but now that one of the doors has already been eliminated, it seems that there is 1/2. So that seems fairly clear that the probability has increased. But why is it the case? Why is there any reason to think that out of the two doors that remain, that it is better to go for the door that you didn't choose as opposed to the one that you chose, right? That's the question, right? So why is it advantageous to switch, or is it, right? That's the question. Greg.
I think it might be advantageous to switch because if you choose a door and you have a goat door, then that means that the game show host just opened the only other door with a goat. So if you switch off of yours, which he couldn't previously pick, then you'd be switching onto the car.
Okay, so you're trying to give some the sort of reasoning behind why it might be a better choice to switch, and
Right.
You are that certainly makes sense. But if you ask anybody, they would say, I'm not convinced, right? So the goal here is to analyze it systematically so that at the end, we will all be convinced of the right answer, okay, whatever it is, okay? So let's do this. So before we proceed, let's lay down some of the assumptions, right? So we want to assume that the car is equally likely to be behind any of the three doors, right? Because this is why we said the original probability is 1/3. The underlying assumption is that it's always, the probability is equal. So we also think that the player is equally likely to pick each of them. So in fact, it is these two, the combination of these two, that makes us conclude that the probability of being right the first time is 1/3. Okay, so this is sort of a implicit assumption we make that when the player picks a door, the host will not open the door that you picked, right? And the host also won't open the door where the car is, right? So the host is going to open one of the other doors, right? You're going to open the door that has a goat behind it and a door that you didn't choose. Okay, so that's another assumption. And if the host has a choice of doors to open, okay, when will the host have a choice of doors to open? If your original choice was right? So then there are goats behind the other two doors that you didn't choose, and the host could have shown you could open either one of them. And we are assuming that the host will just pick either one with the same probability. Okay, so some of these assumptions are not critical. Like this one is not that critical, but this one is important, right? Because this is like an integral part of the rules of the game. Okay, so then when we want to analyze a problem like this, we want to define what are called random variables, outcomes, and sample space. Okay, so random variables are random quantities, right? Are the things for which you want to talk about probabilities, are the quantities that can vary, okay, from experiment to experiment. So what is the door that's concealing the car, right? So that's one random variable. What is the door chosen by the player? That's another random variable, right? And the door opened by the host, right? So these are the three random variables in this particular problem, right? Because there are three doors, and there is a door behind the door containing the car. There's a door that the player chooses, and there's a door that the host opens, right? So these are the three things that vary across, different contestants. So the outcome is a fancy way of saying, what are the values of these random quantities in a particular experiment, right? So in this case, you go to the, you compete in this game show, and then the, what are the 3 things that you see that are applicable in the particular time that you compete, right? So an outcome refers to the values taken by the random variables in any one experiment, okay? And what we are going to do is, if there are 3 random variables, then we are going to use a sequence of 3 to refer to the values of those random variables, okay? So we are going to use the sequence ACB to denote that the car is behind. So that the first thing says, okay, where is the car, right? So it's going to be the value of that random variable, right? So which is the door concealing the car. So this one says it's A. What is the door that's chosen by the player, right? So this particular sequence says, okay, the player chooses C, okay? What is the door that the host opens? That is going to be B, okay? So it is this combination of these 3 random quantities in this particular experiment, and that combination is what we refer to as outcome, okay? And sample space is the set of all possible outcomes. So when we want to talk about probabilities, we are going to think about the space of all possible outcomes and then say, okay, if you're looking for outcome, 1, 2, and 4, then, what is the probability based on the total sample space? So this is all some, setup to sort of set up the terminology that we'll be using. And then once we do that, we are going to use a kind of a tree diagram to display the sample space, okay? So here is a tree diagram showing you the sample space. So this level of the tree, right? The first level of the tree corresponds to the car location variable. The second level is going to tell you about the player's initial guess. And the third level is going to tell you about the gate, the door that the host opens, right? So again, there are 3 variables here, and we are going to show that as a tree so that we can systematically reason through all the possible options, okay? So for instance, this particular path in the tree, what it says is that the car is behind door A. The player initially guesses door A, and the host opens door B, okay? So each path in here, right? This is called a root. This is called a leaf in a tree. And each path from the root to leaf is going to correspond to one possible outcome, okay? So when an experiment is done, you can easily see that, okay, so it can be, the car can be A, B, or C. The player's initial guess can also be A, B, or C. And the door that the host opens will also be A, B, or C. But in many cases, because the host cannot open either the door that the contestant picked or the door concealing the car, right? So because of those conditions, the host is limited. So at the third level, often there are, you see that there are either 2 choices or 1 choice. Whereas in these 2 levels, you see that all 3 possible choices are available, okay? So the reason why we draw these tree diagrams is now we can sort of associate probabilities with edges, and then we can calculate the probability of every one of these, reaching in every one of these leaves. Okay, so let's, okay, so we need one more definition. A set of outcomes is going to be called an event. Okay, so this may seem rather abstract. So let's take an example and try to see how that, how something that we think of as an event, right, corresponds to a set of outcomes, right? So let's say a prize is behind door C. Okay, if that is the event, right? Because then the prices behind door C is captured by all outcomes which have a C in the first place, right? Because remember, the first position in the outcome is telling you where the car is, right? So all we have done is we have gone through the space of all possible outcomes, right? And picked those that have a car in the first, that have C in the first place. And then you can see that there are, these are the 4 outcomes that have a C in the first place, denoting that the car is behind door C. And all we did here is to list those, right? So what we are saying is that in order to figure out the probability of probability that the price is behind door C, we need to compute the probabilities of each of these outcomes. And if we add them up, then we will get the probability of the door behind door C. So now let's pay attention to the one thing that we want to sort of, which is really the event that's of interest to us. And that is player wins by switching. Okay. So let's list all of the cases where the player wins by switching. Okay. So one case is that the car is behind door A. The contestant picks door B. Okay. And then let's say the host shows door C, right? So now if notice that C, because it has been opened, right, it's no longer in contention, and the contestant has currently picked B. If the contestant switches, then they will pick A. And in this particular case, the car is behind door A, right? So this is one of the outcomes where by switching, the player wins, right? And you can go through the rest and convince yourself that they all correspond to winning by switching. And we can, take this tree and mark the cases where the player wins by switching. And let's take, again, one of the paths and convince ourselves of this, right? So this is a path in which the car is located behind door B, right? The contestant picked door A. Okay, obviously wrong, right? Because the car is behind door B. The host shows door C. Okay, so now the contestant knows that the car is not behind C. Okay, and so if the contestant switches, then they are going to switch from A. The only choice they have for switching is B, right? And we know in this case that so in this case, if the contestant makes a switch, then they're going to win, right? So that's why we have marked this with a tick mark to indicate that this is a case where the contestant wins by switching, right? And similarly, you can go through another case like this though. So the car is behind door B, contestant. Okay, maybe we'll go through this. The car is behind door C, the contestant picked, let's say, door B, right? Then if the host shows A, and if the contestant switches, well, they're going to have to switch from B to C, in which case they will win because we know that in this case, the car is behind door C. On the other hand, if you look at this path, right, the car is behind door C, the contestant has already picked the right location of C, right? So obviously, if the contestant switches at this point, they're not going to win. So these are not, winning. The switch strategy wins everywhere where there is a tick mark, and the strategy loses everywhere where there is a cross mark. Okay, so now let's go ahead and compute the probabilities for each of those outcomes, and then we can add them up and then say which one is better. Okay, so let's do that, right? So let's assign the probabilities. Okay, so we already said that car is equally likely to be behind any of the doors. So each of these edges have a probability of 1 by 3, right? So the car could be behind A, B, or C, and we say, okay, there's a 1/3 chance that it is behind A, 1/3 chance it's behind B, and so on. Okay. So we also said that the player makes each choice, equally, right? So this will also be 1 by 3, 1 by 3, 1 by 3, right? So now in this case, the car is behind door A. The player has also chosen door A, right? So the host now can either open door B or door C, right? So those are the two options for the host, which means that the host has, each of these edges has a probability of half, right? So now if you want to talk about the probability of this event, we simply have to multiply the probabilities, right? Because this event A must happen, this edge must happen, and that must happen, right? So the way we do probability of these things is we just multiply the probability. So that gives us 1 by 18, right? So 1 by 3 times 1 by 3 is 1 by 9. 1 by 9 multiplied by half is 1 by 18. Similarly, this is 1 by 18, right? Now, the interesting point here is that in this case, the car is behind A, the contestant has chosen B, right? So therefore, the host has no choice except to open C. So this particular edge has a probability of 1, which means that that outcome has a probability of 1 by 9, right? And similarly, if the car is behind A and the contestant chooses C, then again, the host has only choice of choosing B. So therefore, this path has a probability of 1 by 9. Okay. And what you will find is that this kind of pattern plays out everywhere. So all the tick marked ones will have a probability of 1 by 9, and the ones that have not been marked will be 1 by 18. Okay, so now let's add up the probabilities corresponding to the ones that have a tick mark. So that adds up to 6/9 or 2/3, right? So what it tells you is if you switch, right, then your probability of winning becomes 2/3, right? And if you don't switch, then that corresponds to these 6 leaves. So if you don't switch, then you have a 1/3 chance of winning, which kind of makes sense, right? Because it should be 1/3 because you picked in the beginning, right? Without knowing where the car is, you made a choice among the 3. And so you must have had a 1/3 of a choice. But the surprising part is that if you did switch, your chance of winning went up to 2/3, which tells you, well, of course you should switch, right? Because otherwise you are, it doubles your chance of winning, okay? So the point is that, the problem looks quite confusing at the beginning, but when we systematically draw these tree diagrams, right, and then systematically reason through, the answer is very clear and convincing, right? So we know it is so clear at the end that this is the right strategy. So the point of this kind of exercise is to basically show you that by being methodical and being systematic, you can solve tricky problems involving probability. Because otherwise, just like counting, probability is a topic where we all have an idea of how to do something, but we always end up making mistakes. And so that's why we want to sort of develop a systematic approach that at the end leaves you confident that you have the right answer. Okay, so let us stop here and we'll continue in the next lecture. I will come back in 20 minutes for those people who want to stay tuned for extra help. So one thing I do want to point out before you all drop off is that 80% of the people got there exists a unique, right, the quantifier problem. 80% of the class got it wrong, okay? So it's something that clearly there is some difficulty with that material. So so even if you are not attending the help session, you may want to look over the recording of the help session, because clearly there's that topic where it's not about scoring below average or whatever. It's clear that there is the understanding needs to be improved. So yeah, so that's all. I just wanted to say that you should try to look up that part of the discussion we'll have. So take a 20-minute break. We will start at 45. Okay, 4:45 we'll reconvene here. I'm just going to pause the recording here and we'll just continue in the same Zoom session.